This is the part third for the quick revision guide of fluid mechanics. In this, we will discuss the type of flow. Now, first one is the vortex flow. If the bulk mass of the fluid is rotating about an axis, then this flow is known as vortex flow. And this vortex flow has two types, free vortex and the force vortex. If an additional force is required to rotate the bulk mass of fluid, then this flow is known as force vortex. Otherwise, it is free vortex. For the example, the whirlpool created in the river, it is the example of free vortex, and whereas the flow in the washing machine, in our domestic washing machine, it is the force vortex flow. Free vortex flow is irrotational flow, but the force vortex flow is the rotational flow. In force vortex, the particles are also rotating with their own axis of mass. This is the equation of vortex flow. This is a general equation, that is dP is equals to rho v square upon r multiplied by dr minus rho g dz. In this, v is equals to c by r for the case of free vortex, and v is equals to r omega in case of force vortex. The free vortex is very dangerous flow because as the radius decreases, velocity increases. Now, the equation of surface. Due to this vortex flow, this paraboloid surface is created. So the equation of this is z is equals to square omega square divided by 2g, and this parabola volume is 1 by 2 pi r1 square z1 square. Now, viscous flow. So the flow is characterized by the Reynolds number, and the Reynolds number is inertia forces over the viscous forces, and the value of Reynolds number is rho Vd upon mu. Mathematically, rho is the density, v is the velocity, d is the characteristic length, and mu is the dynamic viscosity. Now the nature of flow. If the pipe flow is there, so if the Reynolds number is less than 2000, then the flow is laminar. But if the open channel flow is there, so if the value of Reynolds number is less than 500, then it is laminar flow. Now, if the value is more than 4000 for pipe flow, it is turbulent flow, and in open channel flow, if the Reynolds number value is more than 1000, it is known as turbulent flow. The remaining portion is known as transition flow, means the value of Reynolds number, if it is between 2000 to 4000 in case of pipe flow, then it is known as transition flow. Now the entrance length. So entrance length of pipe is LE divided by D, that is 0.07 times of Reynolds number in case of laminar flow and 50 in case of turbulent flow. Now the laminar flow through circular pipe, it is also known as Hagen-Poiseuille flow. In this, the shear stress is given as minus dP by dx multiplied by r by 2. R is the radius of the pipe, and u is u max 1 minus r square by capital R square. So capital R square is the radius of pipe, whereas small r is the distance from the center. It may be any point in the pipe from the measured from the center. At center, velocity is maximum, and at the pipe surface velocity is 0. In case of shear stress is 0 at the center, but at the pipe surface shear stress is maximum. Now the discharge can be calculated as pi divided by 128 mu minus del p by del x multiplied by d to the power 4. And this mean velocity or average velocity is maximum divided by 2, half of the maximum velocity. Okay, then the pressure drop in the pipe for a given length of L, it is P1 minus P2 is equals to 32 mu VL divided by D square. Now if the laminar flow is between the parallel plates, it is also known as Cotte flow. So for Cotte flow, the velocity distribution is given by u is equals to 1 by 2 mu minus del p by del x multiplied by ty minus y square. T is the distance between these two plates. Similarly, the maximum velocity will occur at the half of the distance, that is t by 2, that is means the center position. In this, average velocity is 0.6 times of the maximum velocity, and discharge is given as 1 by 12 mu minus del p by del x into tq. In this case, pressure drop for a given length L will be 12 mu VL divided by t square. Now the momentum correction factor is given known as beta. Beta is equals to 1 by AV square integration U square into dA. For laminar flow, the value of momentum correction factor is 1.33 and 1.2 in case of turbulent flow. Now the kinetic energy correction factor, similarly the kinetic energy correction factor, it is denoted as alpha. Alpha is equals to 1 by AV cube integration U cube multiplied by dA. In case of laminar, this alpha is equals to 2, whereas in turbulent flow the kinetic energy correction factor is 1.33. So in this case, the head loss is determined with the help of Darcy-Weisbach equation or the Chase's equation. So Darcy-Weisbach equation is HF is equals to 4F LV square divided by 2GD. In somewhere you can find it F is equals to 4F. So in case of laminar flow, this coefficient of friction is equals to 64 divided by RE. But if 4F is used, then it will become 16 upon RE for laminar flow. And then for turbulent flow, this coefficient of friction is 0.316 divided by Reynolds number to the power 1 by 4. This is the coefficient of friction. So friction loss in a pipe whose end is closed, so it is HF is equals to 1 by 3 FLV square divided by 2GD. Now the Chase's formula is V is equals to C under root MI, where C is the Chase's constant and I can be denoted as tan theta, as you can see from the figure. It is the head loss divided by total length L, and M is the area divided by wetted perimeter. In this case, F is 8G divided by C square. Now the minor losses, that one was the major loss due to friction, and now the minor losses. So minor loss is if the loss due to sudden expansion. If sudden expansion is there, then the formula will be H is equals to V1 square divided by 2G 1 minus A1 by A2 whole square. Loss due to sudden contraction, if sudden contraction is there, then the coefficient of contraction will be there, and HLC must be equals to V2 square by 2G bracket 1 minus CC minus 1 whole square. Then at the exit of the pipe, loss will be HL is equals to V square upon 2G. At the entrance of the pipe, the loss will be 0.5 times of V square upon 2G. Now due to gradual expansion, the loss will be KL V1 minus V2 whole square divided by 2G. And loss due to bend, if the band is there, then the loss due to band will be KV square upon 2G, and the value of K will be 1.2 if the band is 90 degree, and if the 45 degree band is there, then the value of K will be 0. Now the boundary layer theory, it is given by the scientist Prandtl in 1904. According to this boundary layer theory, when the flow of the fluid is developed on some surface, then the relative velocity of the layer which is in contact with the surface will be exactly 0, because at the surface shear stresses are highly dominant. Such a fundamental condition in fluid mechanics is known as no-slip condition. As we move in the transverse direction of the flow from the surface, the shear stresses are decreasing. Therefore, there is a development of velocity gradient. So the zone which is very near to the boundary or surface where the viscous shear stresses are highly dominant is known as boundary layer zone. So this boundary layer zone is there, then the transition zone, then turbulent zone. Then boundary layer thickness is denoted as del. So displacement thickness can be derived, and the formula is del star is equals to 0 to del 1 minus u by u infinity. U infinity is the free stream velocity into dy. Similarly, the momentum thickness, in momentum thickness it is denoted as theta, 0 to del integration u by u infinite 1 minus u by u infinity into dy. Then the energy thickness is denoted as del subscript E double star equals to 0 to del integration u by u infinity 1 minus u square divided by u infinity square into dy. Now the velocity profile over the boundary layer, that is u by u infinity is equals to 3 by 2 y by del minus 1 by 2 y by del whole cube in case of laminar, and now in case of turbulent it is u by u infinity is equals to y by del to the power 1 by 2. Skin friction coefficient is there, that is Cfx is equals to tau 0 divided by 1 by 2 rho u infinity square, and the drag coefficient is CD is equals to Fd divided by 1 by 2 rho A u infinity square. Now the condition for the boundary layer separation, if the adverse pressure gradient is there, then this boundary layer separation will occur. So dP by dx is greater than 0 means if the pressure is increased in x direction, then this adverse pressure gradient occur and the boundary layer will separate. Now there are conditions. If the del V by del Y is less than 0, then it means the flow has been already separated. If the del V by del Y is equals to 0, then the flow is on verge of separation, means it is about to separate. And now if del V by del Y is greater than 0, then the velocity is attached with the surface, so no separation is there. So this is all about the types of flow. In next we will discuss some more topics of fluid mechanics. Now the turbulent flow. So turbulent flow is the shear stress is tau is equals to mu dV bar divided by dy plus eta dV bar upon dy. Eta is the eddy viscosity. Now the determination of this eddy viscosity is very difficult. So Prandtl gives an theory that is known as Prandtl mixing length theory, and according to that we will determine the Prandtl velocity distribution, that is V is equals to V max plus 2.5 V star log E y by r. In this V star is the shear velocity and can be denoted as under root tau 0 divided by rho, where tau 0 is the wall shear stress. So we have two type of boundaries, smooth boundary and the rough boundary. So for hydrodynamically smooth pipe, the velocity distribution is V by V star is equals to 5.75 log base 10 V star y by nu, that is kinematic viscosity, plus 5.5. If the pipe is rough, then this distribution will be V by V star is equals to 5.75 log 10 phi by k plus 8.5. Thank you.